Today we're doing some more Calculus 2 practice problems focusing on improper integrals. So improper integrals are when the bounds, right, the bounds of an integral are something that is messed up. Like we can't really integrate to infinity, right? But what's going to happen is we're going to use this strategy right here where we instead take the limit as t or b or v or any other variable approaches infinity and instead integrate to that variable. That's something we can do, right? So the results of that integral are either going to be infinity, in which the integral is said to diverge, or it's going to approach a finite number, right? And then that integral is said to converge to that number if it actually ends up as a number. So let's just look at an example, right? Obviously, we cannot integrate this to infinity, but we can take the limit as t approaches infinity of the integral from 3 to t of 1 over x minus 1 to the fourth power, right? We can do this integral and plug in t, and then we can take the limit of that integral. These are two skills that we do have. So let's do the integral with a u sub. Set u equal to x minus 1. Du is equal to dx. So I should have a dx in here. Then we have, let's just do the integral over here. 3 to t of du over u to the fourth power. 3 to t, u to the negative 4. Add 1 to the exponent, right? We're going to get u to the negative 3 and multiply by the reciprocal. We're finally going to evaluate that. Well, first, let's plug back in our function. It's going to be negative 1/3. U was x minus 1 to the negative 3. We're going to evaluate that at t and 3. Let's see what we get. So now we have the limit as t approaches infinity. And let's do the, we're going to plug in, let me bring that back down to the bottom. 3x minus 1 cubed. And we're going to plug in t and 3. This is going to be the limit as t approaches infinity. Negative 1 over 3 t minus 1 cubed minus a negative 1 over 3 minus 1 cubed. So let's see, will this approach infinity or approach a certain number? And by approach, I'm referencing that limit. So let's just plug in infinity now. We're going to have a negative 1 over 3 infinity. All of that denominator is just going to become infinity, right? Because we have an infinity minus 1, which is just infinity. Infinity cubed is infinity. And 3 times infinity is infinity. So that's all just infinity, right? And then we have a positive 1 over 3, and 2 cubed is 8. So remember, back to beginning of Calculus 1, dividing by infinity is essentially approaching 0, because as the denominator gets infinitely large, the entire number gets infinitely small, right? 1/100th is much smaller than 1/10, and 1/1,000,000th is much smaller than 1/10. So as the denominator gets bigger and bigger, the number gets closer and closer to 0. So as you can see, the result of this limit is just 1 over 24. So that is what the integral converges to. I'm going to write that it converges. So 2 parts of the answer. They might ask you, first of all, does this integral converge or diverge? Second of all, what does it converge to? Okay, so let's look at another example. How about this one? Well, I see 2 problems here, a negative infinity and an infinity. So we're going to have to split that up. We're going to split it up into 2 integrals and 2 limits. The limit as t approaches negative infinity, and we're going from that t to, now I'm going to split it up at 0. Then I'm going to add the limit as t approaches positive infinity. Since we split it at 0, we're now going from 0 to, and let me change the t. Instead of calling it t, let's call it v, right? Just arbitrary variables of dx. over 1 plus x squared. So this is now something valid, whereas this was invalid. Okay, so let's see. Obviously, both of these just integrate to arctan, right? So we have the limit as t approaches negative infinity of arctan of x evaluated at 0 and t. We're adding to that the limit as v approaches positive infinity of arctan starting at v, ending at 0. So what is arctan of 0? Well, we know that tangent of 0 equals 0, and arctan is just the domain and range flip for tangent. So this 0 comes here, and this 0 comes here. So arctan of 0 is just 0 as well. So this is going to be the limit as t approaches negative infinity, and we have 0 minus t, okay, or I'm sorry, arctan of t, 0 minus arctan of t, and we're adding to that the limit as v approaches infinity of arctan of v minus 0. Okay, so what next? What is the limit? Well, we also kind of need to know the graph of arctan, right? What is happening? Basically, as the range of tangent, I'm just going to draw a little sketch of tangent, right? It's not going to be perfect. Tangent kind of looks something like this. This is also the only interval in which tangent has, this is the only interval in which tangent has an inverse, because in order for a function to have an inverse, it must pass the horizontal line test, and that only happens from this interval from negative pi over 2 to pi over 2, right? In other words, quadrants 4 and 1 are the only places where arctan exists. And when we're saying, what does arctan infinity really mean? Arctan infinity means what value can you plug into tangent to get an infinity value. So like I said, the range of arctan is the domain of tangent, and the domain of arctan is the range of tangent. So as you can see, where does tangent approach infinity? Right at this x value. And we know that tangent has asymptotes at, in this case, pi over 2. And this asymptote right here is a negative pi over 2. So you could say that as tangent approaches pi over 2, its range approaches infinity. In other words, arctangent of infinity is pi over 2, right? So there's a little bit of a trig refresher. What happens as tangent approaches negative infinity, though? I'll write these down. Arctan of infinity essentially just equals pi over 2. And arctan, as you're doing limits of negative infinity, essentially just equals negative pi over 2. We got that from the graph of tangent. So this becomes negative pi over 2 plus pi over 2. So we have pi over 2 plus pi over 2. That's just equal to pi. So this integral is said to converge. So a little bit of inverse trig in there as well. But we had to do two separate integrals, and we just chose to separate it at some arbitrary value of 0. We chose that value because it makes it a lot easier to plug into arctan, because we know that arctan of 0 is 0. So let's move on to another equation. How about this one? Well, there's no more infinities. Does that mean it's still improper? Yes, because you can't plug 0. Well, let's see, right? What is the integral of 10 over x? We're going, just because it's not in the domain of this function doesn't mean anything, because we're plugging these values here into the integral of that function. So the integral of 10 over x just becomes 10 ln x. As you can see, you cannot plug in that 0 into x. ln of 0 does not exist. the graph of ln kind of looks a little bit like that. It's an asymptote at 0. If you plug in 0, there is no output value, so it's not in the domain. So we have to take a limit as t approaches 0. And we're going from t to 5 of 10 over x dx. It's going to be the limit as t approaches 0 of 10 ln of x evaluated at 5 and t. So we have 10 ln of 5 minus 10 ln of t, and we're still taking the limit as t approaches 0. So finally, we have 10 ln 5, nowhere to plug in t there, minus what is the limit as t approaches 0. So we're going to have to think of the beginning of Calc 1, either using graphical methods to solve limits, L'Hopital's rule to solve limits, that was later in Calc 1. But I like to use graphical. We can see that as the graph, or as the domain of ln approaches 0, what happens to the range of ln? Well, this function is going to keep going down and down and down towards negative infinity. So essentially, ln of 0 is really just negative infinity. So we have 10 ln 5 plus 10 times infinity. Well, what is 10 times infinity? That's just infinity. So we have 10 ln 5 plus infinity. That, again, is just infinity. So this integral does not converge. It's said to diverge in this case. Okay, so that's not too bad. Let's look at, and really, like, this limit, it's really 0 from the right? And we have to manually put that there because there is no left limit. So technically the limit doesn't exist, but with improper integrals, we're kind of just ignoring the rules a little bit. And then when you get to like Calc 3 and we look at some more applications of infinity and integrals, they don't even have you bother using the limit notation anymore. This is kind of just a formality is the perfect word to describe it. But let's look at one more. E to the negative x cosine x. So the first thing I see when I'm looking at this integral is two functions being multiplied together. That tells me we're going to have to use parts. And I see that we don't really have a good u or dv, right? Parts is two functions, u times dv will turn into uv minus the integral of v du. This is also a parts wraparound problem, right? Because we don't have a good u or dv, because both of those have infinite integrals and derivatives. So just choose an arbitrary one. Personally, I would rather derive cosine. So I'm going to set u equal to cosine of x. Du is going to be negative sine x dx. That means dv is e to the negative x dx, right? This and this are making up that dv. V is negative e to the negative x. That's just the integral of e to the negative x. So also, we're missing some bounds, right? This is going from 0 to infinity, so that's why we need a limit. It's going to be the limit as t approaches infinity of the integral from 0 to t of e to the negative x cosine x dx. And we're just trying to evaluate this limit right now, right? This limit turns into uv, or negative e to the negative x cosine x, minus the integral of v du. So let's see, the negative will cancel the negative here. And then, once again, this is a parts wraparound problem. We did a lot of that in my integration by parts video. But since we started with the trig function as u, we're going to continue to make the trig function u. Derivative of sine is cosine x. dv is going to be that e to the negative x and dx. There's no more negative because we cancel the negatives. V is again negative e to the negative x. So this integral right here turns to, again, uv sine x negative e to the negative x minus the integral of v du. What was v? Negative e to the negative x times cosine x. Okay, so let's pull this negative out to make a positive, right? So we no longer have a negative. Does this e to the negative x cosine x look familiar to you? Or more importantly, the integral of e to the negative x cosine x. Yeah, that's what we started with. That is this, right? And if we just call this integral I, then we could say that we're subtracting I, right? But I don't want to lose track of my negatives because we are subtracting this integral, right? But that integral turned into all of this. So I do not want to lose track of my negatives. Let's see, I turns into this. And then what we have, let's see, we have I equals negative e to negative x cosine x. That negative gets distributed to this negative and makes it a positive sine x e to the negative x. And then that negative gets distributed to this. Now it's a positive, right? So now we're subtracting that I, which is good. It would only work if that I is subtracted, because now we can multiply it to the other, or add it to the other side. We get that 2i equals sine x minus cosine x e to the negative x. If we factor out that e to the negative x, which means that I, remember I is the answer, is just 1/2 e to the negative x out of sine x and negative cosine x. So this has nothing to do with the improper integral yet, right? Since it's a definite integral, we are evaluating this answer at both t and 0. So we have the limit as t approaches infinity of, we can pull the 1/2 out. We have in 1 over e to the x times sine x minus cosine x. And we're evaluating that at t and 0. So let's see, that's going to be a 1/2. We have a limit as t approaches infinity of 1 over e to the t. And then we have sine t negative cosine t. And then we're going to subtract off the limit as t approaches infinity of, again, 1 over e to the 0 sine of 0 minus cosine of 0. So this negative came from the second fundamental theorem of calculus, right? It's f of b. This was f of b minus f of a, and then I just distributed the limit into like both terms, right? Now let's focus on the right side of this at first. It looks like we have, and that 1/2 was distributed to all of this, right? It looks like cosine of 0, that's 1, sine of 0, that's 0, e to the 0, that's 1. And then we also have, let's also do this limit, right? We're going to get, not as bad as it looks, we have 1 over e to the infinity, right? Well, that's just infinity, times sine of infinity minus cosine of infinity. So this part could be a little tricky, right? When we're talking about limits, though, we know that these ranges between sine and cosine just stay between -1 and 1. But will the sum, or in this case difference of them, ever equal 0? No, because they're 90 degrees off. So for example, look at this. Just because sine ended up being 0, cosine was not 0. And the difference between 0 and that 1 is not 0. This will never be 0. Right? And then we have, well, except for like 45 degrees, but we're not evaluating them at 45 degrees, we're evaluating them at infinity, right? But this is the key. This 1 over infinity, just like last time, will turn to 0. So the point is, even if this thing does equal 0, all of this just turns to 0 is my point. and then we're subtracting off. There's no t's to plug in here. So evaluating that limit is just going to turn to that constant. We have a 1 over 1 and a 0 minus 1. Well, that's easy. Now we have a 1/2 times a negative 1. Negative 1, right? This all just turns to a negative 1. And we are subtracting that negative 1. So now we have a positive 1. So it's 1/2 times positive 1. The integral converges to 1/2. So that was a tricky one. I wouldn't really expect that to be on your test because, like I said, this far into calculus, you've already been tested on integration by parts. They're just wanting to make sure that you set up the formality, right? This limit as t approaches infinity. But improper integrals aren't all that bad. It's just this same strategy, and like I said, they're either going to converge to a number or diverge to infinity. We're also going to look at this convergence and divergence at the end of this review course with series and sequences, and those are a lot of fun. So that is how we do improper integrals.